We now have a system A that is in contact with a reservoir, and the reservoir is basically fixing the temperature at T prime and pressure at P prime. And this reservoir A prime is much bigger, so it has many more degrees of freedom than A. So A prime much bigger than system A. It's a reservoir. For example, an experiment that is performed in the lab would fall into this category. The P prime of the reservoir A prime would be the atmospheric pressure, and T prime would be the ambient temperature in the lab. So in this case, P prime is atmospheric pressure and T prime would be ambient temperature. So as you can see, this is the most common situation one would encounter. And we would have the number of accessible states to system A, a function of some macroscopic parameter y, and the total number of accessible states to the total system A plus A prime, A star, would be the product of the number of accessible states to A and A prime, and the total entropy would be S plus S prime, entropy of system A and entropy of system A prime. So we have the total system A plus A prime is A star, which is isolated. Now, the total energy, since the A star system is isolated, is going to be a constant. So it's energy of system A, E, energy of system A prime, E prime. The sum is a constant. The total volume, V star, which is the volume of system A plus the volume of system A prime, would be a constant. And T prime and P prime, because they are values, macroscopic parameters of a reservoir, they are constants as well. The parameter y, the macroscopic parameter y of system A, has a certain value y0 at a standard macro state of system A, and we can talk about the probability of y having a value y to y plus delta y as the probability of the standard macro state exponential change in entropy of the total system delta S star divided by k, as we have shown in our previous discussion for our study of equilibrium at an isolated system. Probability of a macro state y is p0 times e to the delta S star divided by k. So the same thing applies here. And when we say the entropy change for the isolated system A star, this is the entropy at for a value of y, y equals y, and entropy for y assuming the value y0. And the entropy change, since we have the total entropy equal to S plus S prime, this entropy change is also equal to the entropy change for system A plus the entropy change for system A prime. And the entropy change for system A will be the entropy for y and the entropy minus the entropy for value y0, and the entropy change of system A prime is the entropy at y minus the entropy at y equals y0. So we can see that the entropy change delta S star using our fundamental thermodynamic relation is equal to the heat absorbed Q prime at constant temperature T prime, because T prime is a constant. It's a heat reservoir. So the corresponding change in the mean energy of system A prime is the work done on system A prime plus the heat added on system A prime due to the first law of thermodynamics. And this basically implies the heat added to the system A prime is the change in its mean energy minus the work done on system A prime. So W prime is work done on system A prime when the volume of system A is changed by delta V, which is the value at y minus the value of the volume for the macroscopic parameter value y0 against constant pressure P prime. Okay, now if I look at the change in the volume, because I have V plus V prime equals to V star, a constant. If you look at the change in volume delta V plus delta V prime, this must be equal to 0. Therefore, the change in volume of the primed system is minus the change in volume of the unprimed system. So we have the work done on system A prime for a constant pressure process is minus P prime delta V prime, and this is going to be equal to plus P prime delta V, because delta V prime is equal to minus delta V. So we have the work done on system A prime is equal to P prime delta V. And at the same time, because E plus E prime is equal to E star, that's a constant, we can also write delta E bar plus delta E prime bar is equal to 0. So we can write delta E prime bar is equal to minus delta E bar, where delta E bar is the change in the mean energy of system A for a macroscopic parameter y having the value y minus macroscopic parameter y having the value y0 or y0 to y0 plus delta y. So we can see that Q prime, which was equal to delta E prime minus W prime. So let's take it here, delta E prime minus W prime. This can be written as minus delta E bar, because delta E prime bar is equal to minus delta E bar. And minus W prime is, because W prime is equal to plus P prime delta V, this is going to be equal to minus P prime bar delta V. So this will give us Q prime is equal to minus parentheses delta E plus P prime delta V. So you can see that the change in the entropy of system A prime delta S prime, which was equal to Q prime divided by T prime is minus delta E plus P prime delta V divided by T prime. And since we have delta S plus delta S prime is equal to delta S star, we can see that delta S star is equal to delta S minus delta E bar plus P prime bar delta V divided by T prime, and therefore the change in the total entropy delta S star is equal to T prime delta S minus delta E bar plus P prime delta V divided by T prime. We can also write this in minus parentheses as minus delta E plus P prime delta V minus T prime delta S divided by T prime. And at this point we define G as E bar minus T prime S plus P prime B. So this is called the Gibbs free energy of system A. Gibbs free energy of system A at the specified constant temperature T prime and constant pressure P prime. So T prime and P prime are constants, therefore or P prime bar are constants, therefore we can write for the change in the Gibbs free energy to be delta E bar minus T prime delta S plus P prime bar delta V. So you can see that basically what we have here for the entropy change delta S star, the total entropy change is minus the change in the Gibbs free energy divided by T prime, where the change in the Gibbs free energy is the Gibbs free energy at y equals y and y equals minus Gibbs free energy at y equals y0 or y0 to y0 plus delta y. So or a small range of values. Okay, so we find an interesting result here. The entropy change for the total system A star is minus the Gibbs free energy change of system A, and therefore our statement of equilibrium for this combined system will be the following. At equilibrium, we already know that for an isolated system, the entropy change delta S star is maximum, or we can say that the entropy of the system is isolated system S star is maximum. And you can see that for the entropy change to be maximum, the Gibbs free energy G must be a minimum. So we can state this as follows. The equilibrium situation of a system in contact with a reservoir at constant temperature and constant pressure is characterized by values of its parameters such that the Gibbs free energy of the system is a minimum. So the statement of maximum entropy is equivalent to minimum Gibbs free energy. Maximum total entropy is equivalent to minimum Gibbs free energy of system A. So if we are approaching equilibrium, if we start from not the most probable value of y, so in approaching equilibrium, we're going to have the change in the entropy of the total system, isolated system, delta S star greater or equal to 0. This statement is equivalent to saying the change in the Gibbs free energy of system A is less or equal to 0. And we can also write the probabilities of y having a certain value in the range y to y plus delta y, which was given as probability of the standard macro state exponential change in the total entropy delta S star divided by k. We can equivalently write this as probability of the standard macro state exponential minus delta G, the change in the Gibbs free energy of system A divided by K T prime, the thermal energy. And the change in the Gibbs free energy is Gibbs free energy at a value of y minus Gibbs free energy at a value of y0. So when we are at equilibrium, the probability of having a certain value of y is proportional to e to the minus Gibbs free energy at value y divided by kt, or probability of having a value y is proportional to exponential total entropy divided by k. The maximum probability, which will give us the most likely value of y, which is y tilde, has a Gibbs free energy which is minimum, and the total entropy S star at y tilde is a maximum. So we have an alternative statement for the equilibrium situation in terms of Gibbs free energy. So let's summarize what we said. If we have a system that is in contact with a reservoir at constant temperature and pressure, T prime and P prime, and the experiment, so this could be a very general situation. For example, an experiment performed in the lab where the P prime would be atmospheric pressure and T prime would be ambient temperature. Since the total number of accessible states, omega star, is the product of the accessible states to system A and A prime, the total entropy is entropy of system A plus entropy of system A prime. Total energy is constant, total volume is constant, and probability of a macroscopic parameter of A, let's say y, having a certain value is proportional to exponential change in entropy divided by k with respect to a standard macro state where y has a certain value, y0. The change in entropy of system A prime plus the change in entropy of system A is the total change in the entropy. And remember that entropy is K ln omega. So entropy of system A prime is K ln omega prime, and entropy of system A star is K ln omega star. And according to our postulate of equal a priori probabilities, it's the omega star that determines the probability of having a certain value of y for a given set of states. So we have the change in the entropy of system A prime due to the fundamental relation of thermodynamics is Q prime, heat absorbed by system A prime, divided by its constant temperature T prime. The change in the energy of system A prime is the work done on system A prime plus the heat added to system A prime, first law of thermodynamics. So the heat added to system A prime is delta E prime bar minus W prime. Now the total volume is constant, so delta V is equal to minus delta V prime, and total energy is constant, delta E bar is equal to minus delta E prime bar. So using these two and putting it into the first law of thermodynamics, we see that the heat added to system A prime is minus parentheses the change in the mean energy of system A plus P prime delta V, the change in the volume of system A. And the change in the volume or the change in the energy are for value of y having a y value and y0 value. So minus the y0 value. So this is our standard macro state value here. So the change in entropy of the prime system is minus delta E bar minus P prime delta V divided by T prime. And the total change in the entropy is delta S minus parentheses delta E bar plus P prime delta V divided by T prime. So we see that the entropy change for the total system is with a minus parentheses delta E bar plus P prime delta V minus T prime delta S divided by T prime. We see that if we define the Gibbs free energy of system A at the specified constant temperature T prime and constant pressure P prime as E minus T prime S plus P prime V, the change in the entropy of system A star is minus the change in the Gibbs free energy of system A divided by T prime. And this tells us that at equilibrium, delta S star is maximum, S star is a maximum, Gibbs free energy is a minimum, and in approaching equilibrium, the change in the Gibbs free energy should be less or equal to 0, and the maximum probability, most probable value of this macroscopic parameter y will occur when the Gibbs free energy of system A is a minimum and the total entropy is a maximum.